Hello and welcome to Easy's Pie with Mr. Carpenter. I am Mr. Carpenter, and this will be the multiple choice of the January 2024 geometry regions. In a separate video, I will cover the part 2s, 3s, and 4s. But I just wanted this to be a resource for anyone who might need it. Since I am only one man and a lot of people ask me a lot of questions at one time, and just to be able to have this to refer to might be nice for some people. So let's just get right into it. Number one, which expression is equal to sine of 30? Sine of 30 degrees. So here's what the question wants you to do. Let's start with what they want you to think about. We'll only use, in this course, we only use trig and right triangle. So we know we have a right triangle, which means this is 90 degrees. We have, let's just say that's 30 degrees. And because of the triangle sum theorem, we know that this must be 60 degrees, right? Because 60 plus 30 plus 90 is 180. We got that. So, and let's just give these names. Let's just call them A, B, and C, like we're doing Pythagorean theorem. So if we were to actually look at sine of 30, well, that would be opposite over hypotenuse, which would be A over C. So which of these other expressions would also give me A over C? Well, tangent of 30 would be opposite over adjacent, which is A over B, so it cannot be U. Sine of 60 equals opposite over hypotenuse, which is B over C, so it cannot be sine of 60. Cosine of 60 is adjacent over hypotenuse, which is also A over C. So using that, we have found the equivalent expressions. That's what they want you to do. But if your calculator is in degree mode, right, the sine of 30 is just a number, right? If you type sine 30 into your calculator, you get 0.5 if you're in degree mode. And then if you type cosine of 60, you also get 0.5. So they must be the same, right? So you can just check that out with the calculator as well. Number two, in the diagram of triangle SRA, we draw on line KP so that we have angle SKP is congruent to angle SRA. Always draw these. Draw these always, please. So, since these two lines, since we have corresponding angles that were made here, right, that tells us these lines are parallel, right? If they're parallel, then the corresponding angles are congruent, and if the corresponding angles are congruent, then the lines are parallel. And when the lines are parallel, right, if I have a triangle with a parallel line drawn, then I get to use side splitter theorem, which is part over part equals part over part. Okay, so SK is 10, PA is 6, and SP is 8. They want KR, which I will let be my unknown. Right? So side splitter theorem says that this piece over that piece equals this piece over that piece. So we have 10 divided by something equals 8 divided by 6, and at this point is just algebra. 10 times 6 is 60, 8 times x is 8x. And of course, 60 divided by 8 is going to get you 7.5, which tells me that is number 2. Moving on, number 3, a rectangle is graphed on the set of axes below. A reflection over which line would carry the rectangle onto itself. Remember, when we carry something onto itself, it means we go back to where we started. So which one of these reflections will end with the same rectangle in the same position as it was before? Let's check all these out. Y equals 2 is a horizontal line that crosses 2 on the y-axis. So it'll be this line. If you forgot which makes a vertical or horizontal, you could just graph y equals 2 and check, of course, but ideally that's just something that you know. And if you look, this cuts the rectangle perfectly in half. If I were to reflect this, this point would move over there and that point would move over here. Same thing here or here, right? All these would trade spots and I would be left with the exact same rectangle. So it's got to be number 1. And of course, you could just check out the other ones just to make sure y equals 10. Is this line 1, 2, 3, 4, 5, 6, 7, 8, 9, right? It's up there, so I reflected this rectangle over. We're going to put the rectangle way over there, which we don't really want. And then the other ones, right? 1/2 x minus 3, so y-intercept of -3, slope of 1/2. Get something like that. Yeah, that won't. Yeah. Moving on, number 4, the surface of the roof of a house is modeled by 2 congruent rectangles with dimensions 40 by 16. If you go in, area of a rectangle is length times width, so essentially is 16 times 40. Which is 640 square feet. And there are 2 of these, so that's 640 and that's 640, so we're just going to multiply that by 2. So we're dealing with 1,280 square feet fencing or roof surfacing. And then it tells us that each bundle, right, we're going to buy roofing shingles in bundles, and they're covering 33 1/3 square feet. So for every bundle I buy, I'm going to be able to cover 33 1/3, and I got to be able to cover 1,280. So how many do I need? Well, I'll just take 1,280 divided by 33 1/3. So 1,280 divided by 33. I'll just write out a bunch of threes. And you end up with 38.4. And since it takes 38.4 bundles, I can't buy 0.4 of a bundle, right? That means the minimum amount is I have to buy 39. I have to overshoot it by a little bit. So it's got to be 3. Number 5, which equation represents a line that is perpendicular to this line? Well, I can't identify a line until its y is isolated. In this case, y is not isolated, so I'm going to have to do a little bit of algebra. Not a lot. Very simply, just going to add 3x to both sides. Okay, now I can identify this line's slope, which is 3. I want perpendicular, right? Parallel lines have the same slope. Perpendicular lines have slopes that are negative reciprocals. So 3/1 will be perpendicular to -1/3. So my new line would have to have a slope of -1/3, which only one of these does. So it's got to be number 1. You will ask, what about the y-intercept? Well, the y-intercept doesn't matter as long as it's perpendicular. When we think about parallels and perpendiculars, we tend to only think about slopes. Number 6, I have a right triangle with a reference angle and a missing side. So this is definitely going to be SOHCAHTOA. I want the length of the tunnel. So I want to know what you are. Using 47 degrees as my reference angle. 50, since it's right next to the reference angle, is the adjacent side. And the tunnel is the hypotenuse. So if I reference my SOHCAHTOA, adjacent and hypotenuse go with cosine. So I'm going to make a cosine function. The cosine of the reference angle, 47 degrees, equals adjacent over hypotenuse. And because my variable's in the denominator, right, you can cross multiply if you'd like. Cross multiply and then divide. You'll get that the same way. But we do have that little trick where the variable's in the denominator. The cosine and the variable just switch places. 50 over cosine of 47. And you will get 73.31, which rounds to 73 feet in the tunnel. Number 7, I put a triangle blue on the coordinate grid. I asked for its area. If you go into this trying to do area is 1/2 base times height, you're going to run into a conundrum because you're going to have to find out this height eventually, which is defined as an altitude. And you're going to have a lot of trouble with that. So if you remember, we did have this little trick where I can think of this as a rectangle that perfectly encases the triangle. And then I can find the area of the rectangle, which of course is length times width, which would be 4 times 1, 2, 3, 4, 5, 6, 7, 28. So the whole rectangle is 28, but I also, in this process, make 3 right triangles whose heights are very easy to find because they are on the lines of the coordinate grid. So we have this triangle, which is 3 by, I can't tell, 3 by 4. Of course, the area of a triangle is 1/2 base times height, or base times height cut in half. So we got 3 times 4 cut in half, which is 12 over 2, which is 6. This is 3 by 1, 2. This is also 3 by 4, so that's also going to be 6. This one is 1, 2, 3, 4, 5, 6, 7. 7 by 1. So 7 times 1 over 2 is 3.5. Right? And if I take the rectangle and take out the triangles, I will be left with the triangle that I actually want in the first place. So I can take 28, subtract 6, and subtract 3.5. You are left with 12.5. And that is the answer. You might think you can just count the boxes inside the triangle and try to get its area. I promise you that's going to be much more difficult of a task than you might think it is.
Oh, he's on the phone? No, he's not. He's recording. Oh, my bad, dude.
That was Tyrese, who's now immortalized in this video. Number 8, I take a triangle. I map onto another triangle after a sequence of rigid motions. If I can do that, then I have congruent triangles. Right? When we did, I would translate a triangle and ask if it was the same triangle, and you would say yes. I reflect one is the same triangle. I could rotate it, it's the same triangle. Right? So if they're all rigid motions, which is translations, reflections, and rotations, it's the same triangle. So these are congruent triangles. So I can use these properties, right? So correspondence tells me that CA is congruent to BU. AR is congruent to US. And CR is congruent to BS. And then it tells me AR is 3x plus 4. RC is 5x minus 10. CA is 2x plus 6. SB is 4x minus 4. What's the length of SB? Well, what's it congruent to? We've established it's congruent to CR. So I know that 5x minus 10 is equal to 4x minus 4. And that is just some algebra that I will do now. X equals 6. That's the Poisson answer. Do not select it. The length of SB is 4 times 6 minus 4. And 24 minus 4 is 20, which is 3. It'd be a big shame if you did all that work and then pick 6. Right? Read the problem. Number 9, I dilate a triangle by a scale factor of 1/2. And I map it onto angle CDF, right? If I got from one to the other using a scale factor, kind of similar to the last problem, then they are similar, right? Rotations, reflections, translations, they keep triangles congruent. If I dilate, the triangles are no longer congruent, but they are similar, and similar triangles have all congruent angles. So if angle DFC is 40, then HJG, which will be its corresponding angle, must also be 40. The mistake here is people think they have to cut the angle in half. No, you would cut the side length in half because those are proportional. The angles are always congruent, so that would be 40 degrees. Moving on. Number 10, we have a directed line segment, and we're looking at a partition. So let's go back to that graph and plot these and have a look at it. So we have 5, 7. So let's give ourselves some axes. Remember, they give you this in the back. And let's do that. So one was 5, 7. So 1, 2, 3, 4, 5. 1, 2, 7. And I believe the other was -10, -8. Yes, it is. Okay. So right there. Okay, and this is a line segment, so let's connect those lines together the best that we can. So the first step, if you remember in a partition, is to make a right triangle connecting the vertices. The length of this horizontal line segment right here would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the partition that I want, so let's look at the partition. And normally, you don't have to scroll back like me. You can just cut the graph paper off the perforation so you can look at them both at the same time. It's a 2-to-3 ratio. So let's go back to this. So 2-to-3 ratio means we need 5 equal pieces. And let's see how. So AE to EJ is 2-to-3. So I'm starting at A. So let's go back. So let's label things a little more. That was A. That's J. I'm going to place a point somewhere on here so that AE gets 2 out of the 5 pieces and EJ gets 3 out of the 5 pieces. So if 15 divided by 5 would be 3. So every piece is worth 3. So if AE gets 2 out of the 3 pieces, 2, 3, that's 1 piece. That's 2 pieces, 3 pieces, 4 pieces, and that'd be 5 pieces. So we've divvied it up into 5 equal pieces. Since AE is getting 2 out of the 3, I'm going to place point E here, and I'm going to use the side splitter theorem, draw a vertical line. Point E must go there, and it's at -1, 0. Or -1, 1. What did I do? Oh, I think it might be because I didn't use a straight edge to draw it, so my line is probably a little wonky. You would have a straight edge and you'd be able to plot it perfectly, so it would line up pretty much at -1, 1. So let's go back to that. Yeah, that's the only one that makes sense in that context. Number 11, a tipping platform, which is a right triangle. We have an angle of 30 degrees. The height of the upper end of the ramp, which they've labeled for us, is X, to the nearest foot. And the truck is on a 75-foot long ramp. So that's the ramp, so it's got to be 75. And hopefully he recognizes also SOHCAHTOA. So, using 30 degrees as my reference angle, this would be my opposite side, because it's all the way over there, and my hypotenuse is always my hypotenuse. So opposite and hypotenuse would give me SO, which is sine. So we have the sine of the reference angle, 30 degrees, equals opposite over hypotenuse. And since it's just my variable is being divided by 75, I'll just do the opposite, dividing and multiply both sides by 75. Which is 37.5, which is 4. Get to the highlighter. There we go. Number 12, the infamous right triangle altitude. We know it's going to show up. We have to be ready for it. If I label the altitude X, and that's A and that's B, then if I take the altitude and I square it, it'll be equal to A times B. So using this, let's fill in what we can and solve for what we can't. ME is 6. Let's label these different colors. SM is 4. What is MT? Okay, so I need my altitude. I don't have my altitude. So I have to find it real quick. This is a right triangle, so I just need to use Pythagorean theorem. So we have x squared plus 4 squared equals 6 squared. So x squared plus 16 equals 36. X squared equals 36 minus 16, which is 20. So x equals the square root of 20. Perfect. So now that I know the altitude, I can plug everything in. So I have the altitude squared equals 4 times b. And since it's a square root of a number squared, the square root and the square will cancel out. So this will just become 20. You could always verify that in your calculator. 20 equals 4 times a number. So divide both sides by 4, and 20 divided by 4 is 5. So b is 5. And a lot of people will pick 5. And it's a heartbreaker because it's not 5, because they didn't ask for ST, they asked for MT. So 4 plus 5 is 9. And you are done. Number 13, not one of my favorite problems on the Regents, but it is a good thinking exercise for us. We have a square, so you have to think about what properties does a square have. Well, obviously it has 4 right angles and 4 congruent sides. It also has congruent diagonals that perpendicularly bisect each other. So let's keep that into account as we analyze each one. So first it says ACZ is greater than ZCH. So ACZ and ZCH. Okay, well the diagonals are bisected, which means they're cut into 2 pieces. So those angles are equal. So one angle can be bigger than the other if they're both equal to each other. So that one's gone. ACZ, ASZ. Well, if these 2 sides are congruent, then this is an isosceles triangle, and its base angles are congruent. So one can't be bigger than the other. So it can't be 2 either. Number 3, AZC, which we know is a right angle because the diagonals perpendicularly bisect each other, is the same as SHC, which is a right angle because it's a square. And since they're both right angles, they're both the same. That is a true statement. Just looking at number 4 really quick, AZC was a right angle, is equal to ZCH, which is not a right angle, so those cannot be the same. Number 14, our favorite circles. 2 secants hold hands at point C. Arc DE is 136. Angle C, the outer angle is 44. I want arc FH. If you'll remember, it's outer angle equals big arc minus small arc over 2. The outer angle is 44. Big arc's 136. I don't know what the small arc is, and we're cutting it in half. And this is where just some good old-fashioned algebra comes in. 44 times 2 is 88. Let's subtract 136. So 88 minus 136 is negative 48 equals negative x, which hopefully I'll catch on anyways because I can't have a negative number for an arc measure. So if negative x is negative 48, then x has to be positive 48, which if you divided both sides by negative 1, you would get there regardless. Number 15, a right circular cylinder has a diameter of 8 inches and a height of 12 inches. Which two-dimensional figure shows the cross-section that is perpendicular to the base, passes through the center of the base? We don't have a drawing, so let's make a drawing. We have a right circular cylinder. Here's my cylinder, kind of like a paper towel roll. Okay? Diameter of 8. Height of 12. I'm going to take a cross-section. When we think of cross-sections, it's kind of like we're going to take a sheet of paper and slice this cylinder at a certain point. And we're going to look at the two-dimensional shape that's formed by the intersection of the plane and the cylinder. So I'll use green as the cross-section. The cross-section is going to be perpendicular to the base. So if this is the base, it's got to be perpendicular to it. So we're looking at kind of a vertical sheet of paper, and it passes through the center. Now my drawing is not going to really do it justice, but it's going to kind of do this. You can imagine that paper is just stabbing the cylinder at the moment. And when it does that, we have this portion of the paper that is actually intersecting the cylinder. So it looks like we're creating a rectangle of some sort, so it can't be 1 or 2. Okay. The rectangle has dimensions of what? Well, it's definitely 12 high, and since it's passing through the entire cylinder, right, it has a diameter of 8, so it must be 4. Right, thinking about the whole diameter of the circle being 8. Number 4, I've drawn this line and I have these coordinates. It wants us to dilate this line to make a new line. So let's think about the equation of the old line first. Its y-intercept is positive 4. The slope is rise over run, negative 1 over 1. So the slope is negative 1. So if it was y equals mx plus b, then we have negative 1x or negative x plus 4. So that's what I'm starting with. I dilate it with a scale factor of 1/2. Now we know that dilations create similar figures. So in this case, what would a similar line look like, right? If I change the slope of the line, that it's, for our intents and purposes, it's not really the same line. It's almost like if this angle was drawn and I kept that same angle, right? The angles are changing. This angle is much larger than that one. So the slope needs to be preserved. That's the biggest mistake here, is they will multiply both the slope and the y-intercept by the scale factor. The slope's going to stay the same to preserve that similarity. But the y-intercept is going to be multiplied by 1/2. So keep the slope, multiply the intercept. Right, because the distance, we can think of a scale factor with a dilation of 1/2. We can think of it as, like, it's going to shrink to half its size. But we can also think of it as the distance between the center of dilation and a point on the figure is going to be cut in half. So the distance is going to go cut in half to here. So the y-intercept is now 2, which is what would happen if I cut it in half. So this would turn into keep the slope, negative x, cut the y-intercept in half, plus 2, which would be number 2. Making good progress. Number 17, the toughest multiple choice question on this entire Regents. If I give you a parallelogram with, so let's just draw a rectangle right now and just think about what it might mean later. So A, B, C, D, and those are diagonals. AC is perpendicular to BD. So this parallelogram has perpendicular bisectors for diagonals. That only happens in squares or rhombuses. And it doesn't matter if it's a square or a rhombus. Either way, it's going to have all congruent sides. So I know that these are all the same. AC is 12. Since I know it's either a square or a rhombus, I know its diagonals are bisected. So let's just call this point E. So AE is 6. BD is 16. So BE, so half of that will be 8. And it says it wants the perimeter. Well, the whole idea of finding the perimeter is I need to find out one of its side lengths. Thankfully, I have a right triangle with 2 out of the 3 sides. So I can do Pythagorean 6 squared plus 8 squared equals something squared. I'm going to skip ahead because I know that this is a Pythagorean triple, and that x is equal to 10. So if this is 10, then that's 10, and that's 10, and that's 10, and they all add up to 40. So it's got to be 3. Number 18. You have an altitude drawn here from vertex A. So first, this is looking for an always true statement. So there is a chance that this problem wants us to actually form the 3 similar triangles and make their proportions. I'm going to first look and see if I can get away with not doing that. So we have x, a, and b. X squared equals a times b. Let's rewrite that in terms of their side lengths. So we have AE times AE equals CE times ET. And if we were to divide both sides by AE, maybe we can get somewhere here. Or actually, do any of these formulas, can any of them turn into this when I cross multiply? So if I look at this one, if I cross multiplied, I would get AE times AE equals CE times ET, which is exactly what I had at the get-go. So it's got to be that one. Checking to make sure I got that right, and I do. So yep, it's number 1. So using that right triangle altitude formula, plugging in their official side lengths and trying to see if I can't work it into something that I recognize. Number 19, I have a sandbox in the shape of a rectangular prism. Let's draw that. Okay. No. Something like that. Length of 43 and a width of 30. We use bags of sand to fill the sandbox to a depth of 9 inches. Okay. So if I want the volume of this rectangle, we're looking at length times width times height. So we have 30 times 43 times 9. Which is 11,610. Obviously, that's not my answer. Each bag of sand has a volume of half of a cubic foot, So what is the minimum number of bags that must be purchased to fill the sandbox? So as you can see, it wants my answer in cubic feet. And I didn't realize that, right? And that's okay. So let's instead take these inches and convert them to feet and then find this volume again. So 43 feet, 43 inches divided by 12. So I'm going to write them in red. So we got 3.58 feet. 30 divided by 12 is 2.5 feet. And 9 divided by 12 is going to be 3/4 of a foot. So try that volume again. So we got 3.58 times 2.5 times 0.75. You're going to get 6.7187-ish cubic feet. And now every bag of sand that I'm going to purchase is going to fill half of a cubic foot. So if I take this and how many sandbags am I going to need to fill the sandbox? Well, let's see. Everyone's going to fill as half a cubic foot. So if I divide by 1/2, we're going to get 13.4. Okay. So if I need 13.4 and I only have 13, I haven't filled the sandbox. So I have to overshoot it like I did with the roofing and go to 14. That will be number 1. Number 20, parallelogram EATK. We know it's a parallelogram, so let's just draw a parallelogram. EATK. Diagonals ET and AK. Which information is always sufficient to prove that EATK is a rhombus? Okay, so what do rhombi have? Or what do rhombuses have? What must they have? Well, they must have 4 congruent sides. I'm thinking perpendicular, bisected, diagonals, that kind of stuff. Okay. So I already know it's a parallelogram. So I got this and this. Okay. If I have perpendicularly bisected diagonals, that only happens in a square or a rhombus. And if it is a square, then it's also a rhombus because all rhombuses are squares. So if I have anything to do with the diagonals being perpendicularly bisected, I'm set. So let's just look at each of them individually. EA is perpendicular to AT. Okay. Problem with this is, can I make a counterexample where it's not a rhombus? And the answer is absolutely I can. I can just make a rectangle. So it cannot be U. That is not enough for me to prove it's a rhombus. EA is congruent to AT. Okay. Well, if EA is congruent to AT, AT is congruent to EK, and EA is congruent to KT, right? By the transitive property, all the sides are congruent, and I have a rhombus. So, looking good there. Let's just check out the other ones. ET is congruent to AK. Once again, that happens in rectangles, doesn't have to be a rhombus. This is where just knowing the fun facts about quadrilaterals is going to help you a great deal here. Number 4, ET is congruent to AT. And ET is congruent to AT. I don't even know how to draw that. That tells me the angle isn't right. I'm pretty sure it's not 4. I can't even think of a way to draw that would make any sense. And I'm seeing number 2 and is a sufficient proof. So it's got to be 2. Number 21. Oh, we're definitely working with parallel lines cut by a transversal for sure. ABCD is parallel to EHK. Those are the parallels. We got those. And we have BC congruent to BH. Let's fill that in. Angle NCD is 62 degrees. What is angle PHK? Let's start by filling it as much as we can. Okay? Corresponding angles, you're 62 degrees. Alternate exterior angles, you're 62 degrees. Okay? Vertical angles, you're 62 degrees. Isosceles triangle with congruent base angles, you're 62 degrees. So how do I get to PHK? Well, I see a line here, right? So all these angles have to add up to 180. So we got 62 plus something, give me to 180. So 124 plus something is 180. So it's got to be 56 degrees, which is 4. Getting there. Number 22, also a very annoying problem, but it is doable. So triangle Yeg and Palm. And we want to find a statement that is sufficient to prove Yeg is always congruent to Palm. So let's just assume that they're congruent for the moment, and just for the sake of being able to make a drawing. So Yeg and Palm, and I'm going to be careful with that correspondence. And I know that G is congruent to M. I got that. So let's take each statement and fill it in the triangle and see if it makes a congruent triangle. So we have E and O, Y and P. That's angle, angle, angle. That is not enough to prove a congruent triangle. It can only prove a similar one. So not you. YG is congruent to PM. YE is congruent to PO. That is angle side side, which is the one that we don't like because it makes a bad word. So it cannot be U either. Number 3 and 4 is where it gets dicey. There is a sequence of rigid motions that maps angle E onto angle O. Now, if we can map angle E onto angle O, then they are congruent. And it maps YE onto PO. That is angle, angle, side, which is a valid proof, so it's got to be 3. Just looking at number 4, there's a sequence of rigid motions that maps point Y onto point P, which doesn't do much, and YG onto PM. So I got this, right? And it's got to extend to here, but they can extend out as far as I want, so I can make that counterexample that maps everything to where it's supposed to be, but they're not congruent triangles. So it cannot be 4. 23. This is a proof-heavy multiple choice this year. Which statement cannot be proven? So what does it give us? It gives us that ADB, which looks awfully right-angle-y, but I'm not going to make that assumption yet, is congruent to CEB. So I got these. What else can I find out just at the moment? Well, there's vertical angles for sure. Okay. Since both of these angles are supplementary and they both have a congruent angle, think of it this way. If these are both congruent, right? So I have x plus something is 180 and then x plus something is 180, right? The something that they're being added to make 180 has to be the exact same thing. That's called angle addition. So by that logic, these are also congruent. And in these triangles specifically, since 2 out of their 3 angles are congruent, the third angles must also be congruent because they have to add up to 180 in the first place. That's also angle addition. So I know that these angles are congruent. So have I proven that let's just go to number 2. Have I proven that EAF is congruent to DCF? EAF, DCF. Yes, I have. That is a provable statement. It cannot be number 2. Have I proven ADB is similar to CEB? Well, they have the reflexive angle, angle B, and they have angles A and C. That's two angles. That's similarity. EAF is congruent to DCF. Well, I've proven every angle congruent in the book, so they have to be the similar ones. And by process of elimination, I cannot prove this congruent triangles because I would at some point need to find some side links, and I don't really have much to work with there. Number 24, we have a last one. We have a small town installing a water storage tank in the shape of a cylinder. The tank must be able to hold at least 100,000 gallons of water, and the tank must have a height of exactly 30 feet. So, cylinder. I could go into my reference table, find out that is not 1/3, it is just pi r squared times the height. Okay, so I have a volume, I have a radius, and I have a height to work with. I know the height is 30 feet, because that's what we want. We want a 30-foot height. I do not know the radius of the tank, so I'm just going to let that be x. Now, it's very tempting to put 100,000 in for the volume, but the volume is not the same as how much water that it holds, right? I have 100,000 gallons, and I know that every cubic foot will hold 7.48 gallons of water, right? So 100,000 gallons. I'm going to multiply by a proportion, and since I want gallons to cancel out, I'm going to put gallons on top and bottom. So I have 1 cubic foot is 7.48 gallons. That causes gallons to cancel out. And it's going to end up being 100,000 divided by 7.48. So we're working with a volume of 13,368 cubic feet. And now I have everything I need to find out the problem. So we have 13368 equals pi r squared times 30. Let's divide both sides by 30. In fact, let's divide both sides by 30 pi. Kill two birds with one stone, right? Cancel the pi's, cancel out the 30s. So we're going to have 141.8 equals r squared. And, of course, I just need to take a square root of both sides to get a radius of 11.9. So the radius is 11.9, which we can just round up to 12. Then the diameter must be double that, which is 24 feet. This has got to be 2. It's got to be 2. That was one of the tougher multiple choice I've seen on our Regents. There's a lot of very annoying problems here. But I am very, very, very certain that you all will excel. Take this, learn from it, and I will see you in the next video.